Okay, so good day everyone. We are going to talk about projectile motion, your third topic for the midterms. But before we talk about projectile motion, we need to review free fall. Okay, so free fall refers to the motion of an object under the influence of gravity alone. Okay, so without any forces acting on it like air resistance. The key free-fall formulas are derived from kinematic equations for uniformly accelerated motion, with acceleration due to gravity g, which is typically 9.8 meters per second squared on Earth. Okay. So let us recall these are your formulas for kinematics. V is equal to V naught plus AT. X is equal to V naught T plus 1 half AT squared. V squared is equal to V naught squared plus 2AX. Okay. But in free fall, we use G as the acceleration. So our free fall formulas V is equal to V naught plus GT, Y is equal to V naught T plus 1 half GT squared, V squared is equal to V naught squared plus 2GY. There are two special cases of free fall, namely, one is object dropped from rest, and the other one is object thrown upwards. The illustration here, class, for object thrown upwards is not accurate or is not really the illustration for object being thrown upwards because in free fall we are just going to discuss the change or the motion of a particular object uh, on the y-axis, okay, on the y-axis. So the object thrown upwards illustration here is very closely similar to our projectile motion. But I'm going to use it for the illustration or the introduction for our projectile motion. I will show later on the more appropriate illustration for free fall being thrown upwards. Okay, so let's start with our object from rest. Okay, so let's see. I will mark the beginning of our uh, object. Okay, and I will mark the end. So in here, let us say that this is y naught or initial initial y and final y be y, and this is the change in y. Okay. Change in y is equal to y minus y naught. But in other cases, we let y naught or the initial y to be 0. And so our change in y would only be y. Okay? And take note that the object is dropped from rest, meaning that v naught or the initial velocity is 0. Okay, so let's see if we can derive the special cases, formulas for this special case 1 of free fall. Okay. So the only condition here is v naught is equal to 0. That means v is equal to gt, y is equal to 1 half gt squared, and v squared is equal to 2gy. Okay. And take note that when the object is dropped, we use positive g. Why? Positive g, this means that it is going with the direction of our gravity or the acceleration due to gravity. Okay. And now let's move to object thrown upwards, the second case of our free fall. This is the initial position uh, of our figure. The initial position has bit of a uh, lowering, lowering figure, and we have the position at max height, the release of our ball. Okay, so for an object thrown upwards, this means that we have an initial velocity. Okay, so the person here is readying to throw the object upwards, meaning there is he's building up his energy. Okay, he's building up a force, and in this case, this force will produce a velocity. Okay, not the first special case, because the first special case is just being dropped. Okay, the force is mainly due to gravity. Here we have an initial velocity. Okay, and the position at max height condition here is when the object thrown upwards reaches the maximum height, uh, there will be a final velocity of zero. Okay. And now using those conditions, we can say that uh, the motion is going against the direction of our g. That means that when we're going to derive the formulas here, but we're not going to do that actually because I've already derived it. Okay, so when we're going against the direction of our of gravity, g will be negative. Okay, for this case, for this second case. So this is the initial position. Let's mark the initial position of our ball. Okay, so YO, and that is Y at H max, and that is the change in Y for H max or the maximum height. Okay, the formula for the change in I'm sorry, the formula for Y for the maximum height is equal to V squared over 2G. Okay, so V squared over 2G. That is the third formula on the third formula on the figure hovering above our derived formula. Okay, so how about if we get this? Okay, how about if we get that motion, that full motion? Okay, I repeat, this is an illustration closer to projectile motion. But in free fall, we are only going to discuss the motion along the y-axis. Okay, so if we take that motion, the motion that was shown earlier, okay, we will be having a time to go up and a time to go down. Okay, so this time to reach the maximum height and this time to reach to go back to its initial position is equal shown in our figure. Okay, so T up is equal to T down. And in getting for T up and T down, we're going to use the first formula on the orange curved rectangle. Okay. So T up is equal to T down, which is equal to VO over G. And this T up and T down, this pertains to our time of flight. Okay, so we're going to get the formula for time of flight using this condition. Since T up and T down are the same, we can say that our time of flight is equal to 2VO over G. Okay, so I guess that's all for the review for free fall. I think it's safe to say that we will be discussing projectile motion now. Okay, so a projectile is any body that is given an initial velocity and then follows a path determined entirely by the effects of gravitational acceleration and air resistance. Okay? So the path followed by a projectile is called a trajectory. Let's get the second case of free fall. Let's get the figure for our projectile motion using the second special case of our free fall. Okay. Okay, so our second case of free fall involved a initial velocity. That is also true for our projectile motion. This is this is your projectile, and this is the trajectory. Okay, so this is a very simple figure for our projectile motion. It is mentioned above that uh, the the projectile is entirely affected by gravitational acceleration and air resistance. But if we remove the air resistance, that will be the vacuum. Okay, so see these two videos. Okay, there is a comparison between something that is shot and something that is dropped. Okay, so there is a question here: how does the vertical part of a launched object's motion compare to a falling object with a vertical acceleration? Okay, let's see. Okay, so let's watch it. The red lines there are the points. Okay, the red lines are the points where those two marbles are of the same height. Okay, see, same height. That is the same y. Okay, although the distances between those lines are increasing by the second. Okay, so let's see. Right, so these are the lines that I've mentioned before. Okay, so if they are increasing in the distances between them, this means that the objects, those are marbles. Okay, the marbles are accelerating in the y direction, but I'm not sure if they are accelerating on our uh, x direction because they were both thrown the same up. First, the first one was shot and the second one was dropped. Okay, first one was shot. There was an initial velocity on the first one. The second one was dropped. So the second one follows the principles of free fall, while the other one follows the principles of our projectile motion. For the free fall special case, second special case. Okay, but looking at this, it is clear here that both objects or both marbles were released and both marbles reached the bottom at the same time. Okay, so I think it's safe to say that there is a acceleration in the y direction, which is your negative g, and there is no acceleration in the x direction because our v of x is constant. It is not zero, it is constant. The zero here is a of x or the acceleration in the x direction. Okay. Sorry. Okay, so let's move on to the uh, derivation of our formula. So recall these are our kinematics formulas. I just included um X not here for clear derivation. Okay, so let's input our conditions. AY is equal to negative G, AX is equal to 0, and VX is constant. Okay, so considering X motion, let's first use this one. So V of X is equal to V naught X. Okay, why did we not include AT? Okay, since we're dealing with X motion, the acceleration in the x direction is 0. So 0 times t is 0. So we have our first equation, Vx is equal to V naught x. Okay, next we have this, x is equal to x naught plus Vox e. Again, a in the x direction is 0. That's why the third term in the formula for the recalled formula is 0. Okay, now let's consider your y. Again, we're going to use this. So Vy is equal to V naught y minus Gt. Okay, so Ay is equal to negative G. Just substitute that for A and we get this. Then we have this one next. Y is equal to Yo plus Voyt minus 1 half Gt squared. Okay, so that is our formulas, uh, derived formulas using the given conditions. Ay is equal to negative G, Ax is equal to 0, and V of X is constant. Okay, so let's move on to another illustration for our projectile motion. Let's say this is our xy plane with point O as our origin, and we have a ball. Okay, this ball has an initial velocity, and this initial velocity has components on the x and components on the y. Okay, as previously discussed in our other lessons, when a ball is being thrown or ball, yeah, when a ball is being shot, there are two forces that will be, there are two velocities included in the motion. Sorry, in the motion. Okay, so one that moves uh, towards the concavity of the motion, and one that moves away from the motion's curve. Okay, so let's say we have a ball with an initial velocity at point O. Okay, and we have this also at time 1. We have velocity 1, with its components, and we have our velocity 2. Okay, I notice that we do not have a uh, y component here. Okay, so the y component here is 0 because our ball has reached the maximum height. As stated before in our second special case of free fall, when the particle or the object has reached its maximum height, the velocity here is 0. The velocity that we're talking about in free fall was the velocity in the y direction. And as said earlier, we have a v of x. Okay, so this v of x here is present because we have a constant velocity all throughout the time of flight of our object or particle. Okay, so let's move. We have velocity 3 with its components. And lastly, when the ball reaches the x-axis, or let's say the ground. Okay, so this is the motion of our ball affect, affected by gravity. Uh, Please, uh, change your notes if you're taking them. AY here should be scalar in scalar form. I forgot. AY here should be in scalar form because this is the component of the acceleration. Even though AY is the only component and we can say that A is equal to AY, still AY here should be in scalar form. Okay, so as you can see, I've added our angles here because we have two components and the vectors or the velocities at zero, velocity one, velocity two, and velocity three has their components and it's looks like VO, V1, V2, and V3 are the resultants of their components. And so we can get the direction of our velocities. Okay. And let's see here the illustration of our horizontal velocities. We have your Vx, Vox, we have your V of y, we have your V2x, I mean V1x, V2x, and V3x. Okay. This is the horizontal motion of our ball or the particle. Okay. So as you can see, the V of x, V1x, V2x, and V3x have the same lengths. This means that the velocity in the x direction from the start is equal all throughout the time of flight of our object. Now let's move on to our y, the motion in the y for our projectile motion. Okay, so let's move the points here, 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 there, and there. Okay, so let's get your v of y. V not y, v1y, and your v3y. Okay, so notice that this is just the representation of our free fall second case. Okay, I think that's the free fall for our second case. Okay, so since we will be dealing with vectors, we have your magnitude and we also have your direction. Okay, so let's enlarge this picture. And before I forget, this is our free fall. That is the uh, most appropriate representation of our free fall second case, second special case. Okay, so let's move on to the picture. Okay, so we have VOY. VO is the resultant. A that's alpha, I'm sorry, alpha naught and V naught X. Okay. So using this figure here, we can get the values for our V naught X and V naught Y. V naught X is equal to VO cosine alpha. V naught X is equal to V naught cosine alpha naught. And V naught Y is equal to V naught sine alpha naught. Okay, so we're going to use this and substitute the values onto our derived equations from earlier. Okay, so this is the equation that we got from our first derivation, and this will be the final equations for our projectile motion. Vx is equal to V naught cosine alpha naught x minus xo, or if we just use x, I'm sorry, that's x naught, x not as zero, we can get it, you can say it as x only. X is equal to v naught cosine alpha naught t. Vy is equal to v naught sine alpha naught minus gt, and y minus y naught is equal to v naught sine alpha naught t minus 1 half gt squared. Uh, if you want to know more about the other derived formulas for projectile motion, I suggest that you read our book or that you approach me later on. I will be uploading PDFs for the derivation of other formulas for projectile motions. And I guess that's all for our projectile motions. An example video will follow. So thank you for listening.